I'd like to welcome everybody at the conference, and I'd like to thank the organizers for the opportunity to talk to you. Here are the topics that I'm going to present today. I'm going to have a brief introduction of Decision Systems Laboratory and Bayes fusion, and then present a couple of motivating examples about how hard probability theory is, and that has the impact on what we want to do with graphical models and software for graphical models. Then I'm going to tell you a little bit about an extended family of graphical models, something that not everybody realizes. This is going to be important from the point of view of some of the user interface concepts. Finally, I'm going to go through a somewhat perhaps chaotic list of things that I think any usable interface to Bayesian networks should have, illustrating it from how we did it in Genie. If we have time, we can play a little bit with the software. If we don't have time, perhaps during the question and answer session. This is really an opportunity for me to think back and reflect on what we have done right in the software, and I'm always interested in new things that we can still do right, so I'm definitely very, very interested in your feedback. First, let me tell you a little bit about Bayes fusion and Decision Systems Laboratory. I assume this is the main reason why I was invited to give this talk. So, Decision Systems Laboratory is a group at the University of Pittsburgh that I had the pleasure, the honor to lead over the last 20-something years. Between 1995 and 2015, we developed software for Bayesian networks. We made it available to the community in 1997. And we've had thousands of users, literally. I believe that Genie has become pretty much a standard in academic environments, but it also had quite a number of industrial users. Recently, just last year, we created a company, acquired a license for the software from the University of Pittsburgh, and with pretty much the same team, started developing a commercial version of the software. We have a small team that is kind of spread between two cities, two countries. Our development happens, most of it happens in Białystok, Poland, while research, sales, support is in Pittsburgh, US. As you see this picture, Genie is a little bit trimmed. We have hidden. We got rid. We wanted of some of the functions that we thought were less reliable. They were still university type research projects. So what you see here is the current architecture, which is reliable, fast, of industrial quality. We are doing reasonably well for a beginning company. We are selling. Not yet enough to be rich to support the conference yet, but who knows next year. We decided to keep offering the product free for academic teaching and research, which is something that we are very proud of. We have had many thankful users. We come ourselves from academia, and we believe that academia is contributing a lot to industry. So this is a way of paying back our dues. Let me now continue with the motivating examples for why I think that the user interface is very important. User interface to graphical packages like Bayesian networks. Here is a Bayes theorem, very easy to derive, to prove. It's a theorem in all branches of statistics, probability theory, Bayesian, classical. The ingenious, the brilliant thing proposed by Reverend Thomas Bayes is the following. If we interpret this formula as a way of deriving from a prior probability of an event the posterior probability, then we have a way of changing our beliefs in light of the new evidence. Now that's a simply looking formula, but even this formula gives us a lot of troubles. Here is a simple example that I give to my students whenever I teach these methodologies. Until 1980s, there was a mandatory test for syphilis whenever somebody wanted to get married. To get a marriage license, you had to go through this test. Suppose you and your fiancé go and take the test, and then your fiancé comes back with a positive result. Given that the prior probability of her or him having syphilis is very low, 1 in 1,000, sensitivity fairly high, 0.98, specificity 0.95, both very high for a screening test. What is the probability that the fiancé has syphilis? The calculation is simple. We just plug in the numbers into Bayes' theorem. First, we have to rely on the theorem of total probability to calculate the probability of positive test result. When we plug the numbers, we have the probability of a positive test result around 5%. And then with our prior and the other numbers, we get the posterior of around 2%. Most people are incredibly surprised about that. Why is it so low with such a good test? You see that probability theory is not that easy to comprehend. Most people using numbers like sensitivity and specificity daily, like physicians, when asked about the posterior in this case, give it very high, around 90%. So what is happening? Let me offer, first let me show you that the thought that has always guided me in my work, starting from my dissertation work, which focused on explanations of probabilistic reasoning, and throughout my career and the development of software, I always found very inspiring the quote from Pierre-Simon Marquis de Laplace: "The theory of probabilities is basically only common sense reduced to a calculus." It may sound ironic given the difficulties we have with probability, but I do believe strongly that he was dead right about that. When you do it right, when you interpret it rightly, it is really common sense. So here is another explanation of the calculation that I did for the syphilis problem. Imagine that we have a population of 10,000 individuals. Out of the 10,000, around, well, exactly 10 should have syphilis, and 9,990 should be healthy, the other ones. So every small square represents one person here. So let's screen them. Let's test all of them. Of course, the 10 sick people, almost all of them will test positive. Because the sensitivity is so high, we can expect 9.8 of them to test positive correctly. Well, let's say 10 of them will test correctly positive. Now, with a specificity of 95%, we will have 5% or of the 9,990 false positives. That comes down to around 500. So the pinkish and the red, these are the positive test results. So now, when you look at all the positive test results and your fiancé comes back with a positive test result, only around 2% of them, so the proportion of red to the proportion of all positives, will be diseased. That's much easier to understand, isn't it? So the reason why I'm presenting this example is I want to show you that even the simplest case is hard, but there is always a way of presenting it better. It is much easier to understand, isn't it? Bayesian networks are typically presented in textbooks. If you take any textbook on Bayesian networks, the authors start usually from the factorability of the joint probability distribution. This is the very idea of Bayesian networks. Once you factorize a probability distribution, a joint distribution, you can draw a Bayesian network by essentially leading arcs from the conditioning variables to the variable before the conditioning bar. There are many ways of factorizing a distribution, and some factorizations are preferred over others because in some factorizations we can make use of independencies. So here is another factorization, perhaps a preferred one. Why is it preferred? Well, because it represents the independencies most completely. That's the preferred one. Is it easy to understand? I found it always hard, and my students usually find it hard. Absence of a graph in this means that variables are independent. It's a graphical representation of independence. Here's another way of looking at Bayesian networks. The graphical part of a Bayesian network is a picture of causal relations among the model variables. Here is a Bayesian network that was constructed with the use of textbooks, articles, and experts. It is pretty much following a causal structure. Let me blow up a little bit of it. An arrow between diabetes and obesity means that diabetes is a risk factor for obesity. It's a cause, one of the causes of obesity. Obesity is a causal factor for hepatic steatosis, which is one of the diseases of the liver. In short, an arc denotes a causal influence. That's another way of viewing Bayesian networks. And there are also good empirical reasons for viewing them that way. I'm not sure I will be able to get into that, so let's just take it as a given. Let me follow this up with discussing an extended family of directed graphical models. The reason why I'm telling you about this is that many people don't realize that, and knowing that family will have an impact on how we perceive Bayesian networks and how we can build good interfaces to them. Here is a very old modeling technique, a system of simultaneous equations. In this case, we don't have really a lot of time to get into the details of this equation, but this system describes university operations. There are three what we call core equations describing mechanisms acting in the university environment, like class size, faculty salary, and student-teacher ratio. And then we have also equations for exogenous variables. We have 10 equations with 10 unknowns. The system can be solved, and given these exogenous variables, we can calculate the class size, faculty salary, and student-teacher ratio at the university. The thing that I wanted to say now is that there is a way of viewing this system in a graphical format. Together, these equations determine the structure of the model. It was explicated by my advisor, Herb Simon, in the early 1950s. It's a great thing to realize that there is a structure here, and under certain circumstances, this structure can be also given a causal interpretation. Another member of this family, if you think about this, are spreadsheet models. They can also be viewed as graphs. A spreadsheet model can be viewed as a system of simultaneous equations, the same way we viewed the system of simultaneous equations in the previous example. The graphs, if you draw them from a cell to another cell, whenever the other cell uses an equation, a formula that uses the cells, right? We have a graph. Any practical spreadsheet, of course, would essentially get a spaghetti of connections, too difficult to work with. Systems of simultaneous equations and spreadsheets are not the best we can do. Directed graphs are much, much better. A summary slide: systems of simultaneous equations and Bayesian networks are members of the same family, and they both can be pictured by acyclic directed graphs. What are the implications of that? Here's one implication. Here is a system of simultaneous equations that composes a model of heating and cooling of buildings. There are two core equations represented by this and this variable, and a number of exogenous variables specified by continuous probability distributions. Here are the equations. Here's a model turned into a Bayesian network by means of discretization. Now we can work with this model as we would with a Bayesian network. We can observe the distributions by means of what you could call histograms or bar charts that show the probability of over the intervals, over the domains of the variables. Here's another place where I think the equation-based view is very handy. Here is an illustration from Kevin Murphy's dissertation on dynamic Bayesian networks. It represents it's taken from a paper by Kierulf, represents a model called mildew, describing a dynamic system where we have a mixture of normal influences, like from mildew to LAI, or LAI to micro, or from precipitation to micro, and then we have temporal arcs. Temporal arcs are drawn between two different instances of this network. We can imagine that as this is the network at time t, this is the network at time t plus 1. But boy, what do you do when you have influences of higher order, like second, third, or 10th? You would have to draw this as many times as there are time orders, arrows of a different time order. Here's a better way of picturing this. If you get the inspiration from systems of simultaneous equations. In a system of simultaneous equations, we are dealing with variables. Well, when you have variables, then one representation of a variable should be enough. Variables take part in different equations, and this is pictured here. A micro as an equation, taking three variables that are parents of this variable micro. Micro is the fourth, so here we are dealing with an equation involving four variables. Whenever we are dealing with a temporal arc, we are dealing with a differential equation. An arc of first order, it's a first order differential equation. So mildew involves it's a differential equation that has that depends on differentials of micro, fungi, and mildew itself, etc. This representation is much simpler. We don't need to have multiple representations of variables. Adding arrows of higher order is very easy. You just add them to this picture. No special gymnastics needed to facilitate the two-slice representation. We can you can see it in the layout. We don't need to flatten it to make it easier to see the temporal arcs. We just make them use the layout, whatever layout is handy, useful, understandable. Higher order influences means just new arcs within the same set of variables. So now this part of the talk is a set of ideas that I would like to present. They may not be necessarily very orderly, but I think they are all interesting and useful. The main idea is that graphical user interface to Bayesian networks should stimulate insight. The user is the ultimate decision maker. She will not follow any advice without understanding it. Misunderstanding the problem and the model can lead actually to a performance that is worse than unaided performance. The same happens with experts. They also need to manage the complexity of the model and their parameters. The first thing that is, I think, very important is navigation. There must be various ways of viewing a model. What you see here in this screenshot is a graphical view, something that you are familiar with, but at the same time a tree view. Tree view is easier from some perspectives. For example, you can list nodes alphabetically. You can find them easily. Users have different preferences, and we need to address them. Sometimes there is just not enough room on the screen. They talk about screen real estate in GUI design. The screen real estate can be addressed by a variety of techniques. For example, you can increase or decrease the size of the graph. That way you can see the entire graph on the screen or just a piece of it. Genie has also a full screen mode. If you click on that, if you use it, then there is nothing on the screen, just the model, just the graphical part of the model. There's also transparent mode. That is useful when blowing up, increasing, decreasing doesn't help. Then moving around this small window that is in the transparent mode allows you still to see what is under. Model is a document. A model can be used by other people who read it or by ourselves after a while to see the important decisions and the assumptions that we have made. What you see here is on-screen comments. They can be edited at any place. In addition to on-screen comments, it is also useful to make annotations. I was very much impressed by this yellow sticky notes, and then at some point decided to use that idea anywhere in the model. So you can add the notes, on arcs, or states, or individual probabilities. When you hover over them, you will see the annotation. Submodeling is a good technique, great technique, developed by Max Henrion, one of my advisors, and his programmer Brian Arnold. They essentially, what submodels achieve is hiding the complexity of the model and make the model manageable. You can open individual submodels in new windows. You can navigate through the graph by clicking on these small triangles and moving back and forth along the actual arrows of the directed graph. Searching for text is a great thing that is really a must. When the model becomes very large, and I'll show you a couple of large models on the screen, sometimes it is very difficult to find the node that we are looking for. Searching, which can go through nodes, through annotations, through on-screen comments, double-clicking on any of these items found brings you to that item in the model. One thing that is, I think, a very interesting technique, very useful, is displaying the strength of connections. Because we have a full joint probability distribution, we can easily derive the strength of the connection based on concepts such as change in entropy or expected change in entropy, cross entropy pairwise. And there are actually several different ways of deriving the strength of connections. Strength of connections, the thickness of arcs, allows for verifying the expert's intuition after the model has been constructed. Another application is when we learn a model from data, we can see what is going on in the domain and which connections are the strongest. Learning, both structure and parameter learning, are a must in a good Bayesian network software. We can use learning for data analysis, but also for causal discovery, which is really a very cool area. I wish I could talk about it for an hour or more. Sensitivity analysis is another important technique. Because typically models contain many parameters, we don't want to spend equal amount of time on all of the parameters. What we can do is we can find out which of the parameters are important and then invest more time in getting them to be more precise. So the question is, what should we pay particular attention to? Here are the parameters. When we run sensitivity analysis, we see where the important parameters are. These are the red and pink and lighter pink nodes. We can examine them more closely, looking at the maximum and minimum sensitivity in a node. This number is essentially a derivative of the posterior probability over the parameter. We can also examine individual conditional probability tables and see which of the distributions, which of the numbers are important. We can view these parameters also in a graph that is called tornado diagram, showing us how the posterior changes as the value of the parameters change. I think that a good GUI should hide the unnecessary technicalities. Sometimes I see in computer software for Bayesian networks a compilation phase and an execution phase. That's very much a computer science view. Why would a user care about this? The user constructs a model and wants to use it. Triangulation, junction tree, I beg your pardon, what is that? Another thing that I think is useful to do is, what we've done is we keep the model under construction always correct syntactically. Whenever you add a node, it already has two states and a uniform distribution, which makes it syntactically correct. It's still useless, but it's at least syntactically correct. You can detect any possible problems with the model, for example, cycles, wrong ID, etc., at the time of building the model. You don't need to have a special phase that checks that. People love feedback, and feedback is always good to give. The small icons show the status of a node. We can show that a node is updated, needs updating, it's observed, it has virtual evidence, it's implied, etc. We also point out useless arcs. Useless arcs are such arcs that are not necessary because they do not make any difference in the conditional probability distribution. So in order to show a useless arc, you need to look at the conditional probability table. But you can read it out of there. Two useful operations that are especially useful in the model building phase: arc reversal. Sometimes it's more convenient to elicit probabilities in one direction, but use it in the other. For example, the other one is the causal direction, but maybe it's easier to get the numbers in the diagnostic direction. We can reverse the arc temporarily, enter the parameters, and then reverse the arc to get the final model. The models are equivalent, the only difference is the arc. You can also, sometimes you may want to use an operation called marginalization. You want to get rid of a node, of a variable, but you don't want to change the joint probability distribution over the remaining variables. In this illustration, the variable worth is marginalized. By that, you get arrows from variables asset and income coming to the future income, and no longer variable worth. This is a destructive operation. It is difficult to come back to the original model. Another thing I think that is important is modeling freedom. If you have a continuous model like this one, here's a definition of a node with a continuous distributions and an equation, we offer complete modeling freedom. We don't worry about is something computable or not, because the world is not does not consist of only linear relationships with Gaussian noise. It's not the user's worry how to calculate in this model. We take care of it using stochastic sampling, Monte Carlo methods. But the user should not worry about restricting her mind to just things that are computable. Now, two examples of specialized interfaces. Bayesian networks graphical interface, it's good for experts, perhaps, but not for users. So users should see the model, the system, the way they should see, the way they are used to seeing. Here's a diagnostic window, diagnostic interface. Here are all the possible problems, in this case diseases, it's a medical model. Here are the possible observations. Here are the observations that we have already made. Possible observations are rank ordered from the most to least informative. This can be calculated. It's a cross entropy between the observation and the diseases. Here's another interface where you cannot even easily figure out that Bayesian networks are underlying. It's a website where SMILE, our reasoning engine, is the primary engine. This is a diagnostic site allowing people for self-diagnosis. They don't need to know, they don't know that there are Bayesian networks under. Well, perhaps with the accuracy only. Bayesian networks work. Here's one of those big models that we have, that one of our users was using. 2,127 variables. Look at the number of arcs, independencies. This is a blow-up of part of this model. It's a spaghetti. It has only 2,000 parameters because of use of canonical gates. But if you were to model a joint probability distribution over 2,100 variables, you would need that many parameters, 10 to the power of 632. That's much, much larger than what we believe is the number of atoms in the universe. Why am I showing that? I just want to say that what one would expect from a Bayesian network package is speed, efficiency. They have to be responsive, they have to come back within a fraction of a second. And SMILE, I'm pleased to say, comes back within a fraction of a second after updating of this model. A few slides on CPTs, because this is one of the difficulties in Bayesian networks interfaces. We found that horizontal orientation is much more intuitive to people. There's software with horizontal and vertical. I suspect vertical the tables are much easier to implement, the GUI, but these are more intuitive. No matter how hard it is to program this, to code, this should be done, I think. Shrinking and expanding parts of CPT. When the CPT is very large, it's handy to shrink part of it. Clicking on this plus and minus shrinks and expands the CPT. Then you can see it on the screen in one piece. Changing the order of states. I wonder how many of you have had a situation where elicitation of probabilities is counterintuitive because we don't, I guess the order of the parents is kind of funny. It violates the temporal or causal order. It should be easy to change that order. In Genie, you can just click, drag, and drop in the new position. This took us a few weeks to program. It's not trivial, but it's still worth it. We should be able to do it as users. The same with changing the order of states of a variable. That should be also possible to do. I mentioned this idea that everything is correct in a model. The CPT of each node is always correct. We've made it it was a design decision. You cannot exit the dialog where you enter a probability distribution if something is incorrect. You can see what is wrong by hovering over those signs. This number is too big, the sum is not 1, etc. The user knows what to correct. Elicitation of probabilities is much easier with a graphical interface. Not always, but typically it's much easier. This is a device known as a probability wheel. Here is a bar chart showing the same thing but in a different way. They are good for different purposes. Canonical models is a must. The reason why that locomotive diagnosis model of 2100 variables had only a few thousand parameters is that it relies very heavily on canonical models like noisy OR and noisy max. They are a must for any Bayesian network software. I cannot imagine constructing real models without it. I believe that we are running short of time, so let me finish the talk, and we can always go back to the software if there are any questions. Bayesian probability theory works. There are plenty of successful applications that solve real problems. 21st century is called the century of Bayes, but also century of data. I believe that the main bottleneck in this business, just like in many other cases of automation, are human experts and human users. The user interface is very important. Good user interface is a must. It saves time. Now that we are a company, we have to translate it into money. It is really money. There is a big difference between spending 20 hours and 5 hours on a model. And it also leads to better quality models. A good interface allows to see what is wrong with the model at a very early stage. That saves a lot of time. And again, I'm kind of embarrassed to say, time is money, and quality of the model is also money. This is the last slide. Here are different ways of getting in touch with us at the company. Conference special. If any of you wants to buy Genie, we are offering 50% off of perpetual licenses and 30% off annual licenses to conference participants until 15th of January. And we will donate 10% of the total sales to the organization. The same discount for the academic license, which is of course a joke because academic licenses are free of charge for teaching and research use at academic institutions. Thank you very much.